Before going further in ACID properties with Athena, let's take a quick recap of Lakehouse. So what is Lakehouse? And again, before talking about Lakehouse, of course, we'll have to discuss data lake. And on AWS, S3 is considered as a data lake. So what is data lake? It contains the raw data wherein we basically dump all data in its raw format. For example, we can have CSV files, we can have Parquet files, we can have ORC files, we can have Excel sheets, so on and so forth. So in data lake, we just dump the data, and after dumping the data, we use it for further processing and store the formatted or processed data also. That is what data lake is. So for example, in S3, we store, let's say, data which is in CSV, but typically for in most of the cases, we'll not be using the CSV files. We'll be using Parquet files or ORC files or some other file format which would be optimized for either Redshift or Athena, etc. So what we do is that we get the files in CSV format, then let's say do some processing using Spark or Glue or something else, and then we store it in Parquet format, that too also in S3. So that's why S3 is considered as a data lake wherein we keep all format of data. It does not mean that we'll be only having CSV, Parquet or these type of file formats. We can have PDF files also, we can have images also, we can have video files also. So let's say images and video files can be used for machine learning or AI processing. So we can use S3 to store those file formats as well. And again, that's why S3 is considered as a data lake. Now there are of course certain limitations of data lake, and one of the major limitation is that single row update, insert, delete are not possible. Now I'm talking about CSV, Parquet, ORC, JSON, etc. files. So if you store the data in any of these format, you cannot pull out a single row, update it and store it back. So what we have to do is that we have to download the entire file, use some programming language or some framework like Spark to update that particular record and then upload the file again. So this is a very big limitation of data lake, that single row or even multiple row update, insert and deletes are not possible. So if you have, let's say, millions of rows and you want to update, let's say, only a few hundreds of rows, then you'll have to download the entire file with millions of rows and update those hundreds of records and then upload the file back again. So of course you can imagine the amount of overhead that this kind of topology has. And so far in Athena also, we have not seen any data modification. So far I have only shown you the data selection or data fetch only. Now this limitation is handled by something called open table format, and there are three types of open table formats: Iceberg, SerDe and Delta Lake. So what does open table format entails? It enables single or multiple row update, insert, delete on data lake. So we get data warehouse like feature on a data lake. So whenever we use any open table format with our data lake, we call it as lakehouse. We use Glue data catalog and S3 files for these open table formats also. So this is how, let's say, our data catalog, and we had created this 3IAM Athena DB, and these were the tables that we created, like orders, customers, order items and products, and all these tables are pointing to some S3 buckets and folders, and this is basically the metadata. And so far we have not been able to, or at least I have not shown you any update, insert or delete process happening on these tables. And also you can't do it because all these files are stored in Parquet format or ORC format or CSV format or some other format. So using those formats, we cannot implement lakehouse architecture. So to implement lakehouse architecture, we need one of the open table formats. It can be either Iceberg or SerDe or Delta Lake. As I already mentioned that for these tables, there were no insert, update or delete operations that we performed. So I'll talk about Iceberg only. I'll not discuss SerDe or Delta Lake because Iceberg is pretty famous in the open table format or in the lakehouse world. AWS has also pretty nice integration with Iceberg. Not only AWS, other cloud providers also have pretty nice integration with Iceberg. So let's talk about Iceberg tables. Okay, so to define the open table format, irrespective of Iceberg, Hoodie, or Delta Lake, what it does, what it entails, it provides metadata structure to enable row level changes in data lake, meaning that we can make row level changes, and those row level changes are handled by open table formats using a metadata structure. So whenever we make any changes to the table, those changes are basically captured by the open table formats, in this case Iceberg, in a certain metadata structure. So let's go ahead and see what this metadata structure is. So this is how the architecture is. We have something called Iceberg catalog. So Iceberg catalog in AWS would be, of course, glue catalog, and then we define the table in that catalog. So we can define an Iceberg table in glue catalog also. This table basically points to something called a metadata file, and a single table can have multiple metadata files. So here I'm showing you only 3 metadata files, but there can be multiple metadata files also. Of course, we'll go deeper into the architecture in the next slide, but this is the high level overview. And the metadata files are stored as some name followed by .metadata.json. So the metadata files are stored in JSON format. Now, as I said, it contains the table schema, it contains tables partition information, and something called snapshots. Now, this particular table that I'm showing you, it can actually point to multiple metadata files also, but typically it would always point to the current metadata file. Then these metadata files, or basically one of the metadata file or the current one, would point to something called a manifest list. This manifest list would contain information about manifest files. The manifest lists are stored as snap dash followed by certain characters, then followed by .avro, which means manifest lists are stored in avro files. A single metadata file can point to multiple manifest file also. So here if you see, we have metadata file 3, which is pointing to manifest list 2 and manifest list 3. Metadata file 2 is pointing to manifest list 2 and manifest list 1, and metadata file is only pointing to manifest list 1. So manifest list again points to manifest file, which contains information about data files, and the structure is some random characters followed by m0.avro. So manifest files are also stored in avro format, and these manifest files basically or finally points to the data files, which contain data along with something called delete files. At a very high level, delete file is something which will capture the data changes or row level changes, and then these files would be stored along with the main files. So let's say you have a 100 GB file and you are making change to only, let's say, 5 MB of data, then the size of the delete file should be approximately 5 MB, and it will be stored with the 100 GB data file. And there are processes of merging these files together, and which is done by Iceberg automatically behind the scenes. So now this entire thing, starting from table to the manifest list, so the table, the metadata file, the manifest list, and the manifest file, all these are basically the metadata structure that I was talking about. And this is how, using this metadata structure, all the row level changes are captured. Now let's go a little deeper into the architecture. So as I said, we have data catalog or Iceberg catalog, which will be basically glue data catalog in our case. And here we define the table using the create table DDL statement. Now whenever we create a table, it creates something called a pointer in the metadata itself. Now this pointer would basically point to something called a snapshot. So let's see how this snapshot is. So let's say I am running a create table statement, And what would happen is that it would create a metadata file first, and along with it, it will create metadata.json file. And so the location would be data lake. And when you do hands-on, I'll show you that in that particular location, we'll be able to see the metadata.json file. And it would create a snapshot, so which is basically BS0. And this snapshot is basically telling you that the table has just been created. And once this metadata file is created, after we create the table, the pointer in the table definition would point to this particular metadata file, which contains snapshot 0, meaning that this is the first snapshot of the table when we create the table. Of course, after creating table, what we do, we insert records into the table. So then what would happen, the records would be inserted in S3 Parquet file, which would be stored in S3. So this Parquet file would be the data file, and Iceberg would create a manifest file which ends with m0.avro, and this manifest file would point to the Parquet data file. And then Iceberg would also create automatically a manifest list which will start with snap and end with .avro. And this manifest list would point to this manifest file. So manifest list would contain the details of all the manifest file, and manifest file would contain details of all the data files that this particular snapshot is holding. So then it would create a metadata file, and a new snapshot would be added, which is S1. So S0 would also be here, but S1 would be created. What this snapshot would point to, it would point to this particular manifest list. So essentially, S1 snapshot is eventually pointing to this particular data file where you have just loaded the table. Of course, there can be multiple data files, not one. So there can be 10, 15, 50, 100 Parquet files also. But this snapshot in the metadata file would point to the manifest list, which would contain the list of the manifest file, which would contain the list of the data files, and these are the data files where actual data would be stored. But now if you see, this table definition earlier was pointing to the first metadata file. Now Iceberg has created a new metadata file which contains snapshot 0 and snapshot 1. So again, snapshots are not backups. These are basically pointers at a particular time. So S1 points to the data file eventually for a particular time. And this pointer, along with the table definition, it would point to the new metadata file now. Now let's say after that we do inserts, updates and deletes, etc, etc. Of course, it will add or remove records or update records, and those will be affected or those will be captured in the data file which is stored in Parquet format. And once the files are created, it would also create a manifest file or one or more manifest files, which will again create manifest list, and eventually it would lead to creation of a new metadata file with a new snapshot S2, which would point to this particular manifest list. Okay, now let's say you make some updates or make some deletes. So what file it would contain? So basically what would happen is that we have a concept called delete files. So delete files would contain all the row changes that we have done in the Iceberg table. So if you do an update is basically a combination of delete and insert. So deletes the old records and inserts a new record. So insert is basically an insert. Let's say we insert a single row or maybe 5 or 6 rows. All those rows would also be stored in something called delete files, or you can think of it as delta files, which contains only the data changes. Now this manifest file would point to the actual file also, which is basically this one, and then additional delete files where all the data modifications are there. For example, let's say the actual file is of size 500 GB and then we change 1 GB of data, then there would be actual files with 500 GB size and delete files with 1 GB of size. So this particular manifest file would point to the actual 500 GB file and the 1 GB delete files also. And of course, in the table definition pointer, the pointer would change. But before that, the snapshot one would still keep pointing to the previous version manifest list, and the pointer of the table definition would change to the metadata file. So let's see this in action. So what will I do is that I'll create an iceberg table, and after creating an iceberg table, I will basically load records in that iceberg table from an existing table, and then we'll make some modification. I'll insert only one row, then maybe I'll delete one row, and then I'll update one row. And we'll see how these delete files, manifest files, and the manifest lists are created along with metadata file also. So here what will I do is that I'll create a folder and I'll do the testing on order items table. So let me create order underscore items underscore iceberg folder, and we'll use this folder as the location of the iceberg table. So let me create this. So we have this order items iceberg created, and I'm creating this table order items iceberg with order underscore id, product underscore id, and the location is the folder that I have just created. But in table properties, I'm mentioning the table type to be iceberg. This is very, very important. Okay, so we'll have to mention this table type iceberg, then the format is Parquet, the compression is snappy, and there's something called optimize, rewrite, delete file threshold is 2. But before that, let me go ahead and create a database. The name of the database would be iceberg, part, and bucket, because I'll be talking about partitioning and bucketing also. So it is done, and the database has been created, iceberg, part, bucket. And what am I going to do? I'll be creating this particular table, this particular iceberg table, pointing to this location. Now, let me first show you that under order items iceberg, I do not have any objects. All right, so I'm going to create an iceberg table in that particular location. So let me go ahead and create this, and after the creation is complete, and now if I do a refresh, I can see metadata has been created. So what is this metadata? If I click on this, okay, so we have this JSON file, which is basically metadata.json. So what is metadata.json? Metadata.json is the metadata file that has been created the moment I created the table, and nothing else is there, and it contains the snapshot 0, and of course the table definition points to this metadata file. We can't see that anyway. So if you go to the glue data catalog, I should be able to see the new database, and if I click on this, this is the table order items iceberg, and this is the database, and if you see the location, it contains the name of the folder. So the pointer is maintained internally by iceberg. Of course, I can download this file and take a look at it. Let me download this, and I have opened the file. So if you see here, there are a lot of information, but let me try to tell you some of the information, not all. So this is the table UID, which is basically the unique identifier for the table, and also talks about the location. And last updated, last column ID is 2. This is the current schema ID, and what the schema contains, it contains order ID and product ID. The table is not partitioned, and these are the properties. It is Parquet file, snappy, something called delete threshold, object storage path, etc, etc. That's all. And the current snapshot ID is -0, right? So this is the metadata file that has been created. Now what will I do is I will keep the last modified location, so it is 2250. Okay, so let me go back to the folder. So only the metadata folder is there. Now what will I do is that I'll insert a record into this particular iceberg table. And before inserting, let me go ahead and create this order items table also on CSV, because it is there in a different database. I'll create it here also. Again, it is pointing to the same dataset. If you see, it is pointing to 3IAM Athena dataset, then Athena tables and order items. And let me do a select count. So it contains approximately 200 million rows. So now let me insert records from this particular table to the order items iceberg table. So it will take some amount of time for the query to be executed. It will scan some data, I think 3 or 4 GB of data, and after that the files will be inserted here in the Iceberg table. So if you see, currently only 3 GB of data has been scanned and the runtime was 14 seconds. And now if I go back, so do a refresh, there should be a data folder. But let's first take a look at the metadata folder. Earlier we had only one object, now we have 4 objects, right? So if you see, a new metadata has been created. This is the time, 22:55:32. This is m0.avro. So what is m0.avro? As I had shown you, when we did the insert, it created a data file and it created a manifest file. So the m0.avro is the manifest file which is pointing to the data file that has been created in the data folder. We have not seen the data folder yet, but we'll take a look at it. And then one more file should be created, which is the manifest list. It starts with snap and ends with .avro. And then there should be one more metadata file which should point to this particular manifest list. If we look here, we have one more metadata file. This is the newer one at 22:55:32. This is the manifest file which ends with m0.avro, and this is the manifest list which starts with snap and ends with avro. Let's take a look at this particular metadata file. Okay, I should download it rather. Okay, so again the table UID, this is the location, last updated timestamp, this is the schema. And if you see here, this write object storage path is S3 Athena object items data. It was there earlier also. And there are a few other things, right? So we have this snapshot. This is the sequence number and this is the snapshot ID. Snapshot ID is ends with 31298. So this metadata file is pointing to this particular snapshot. And if I look at the files, this snapshot ID is also 031298. So it is matching with our metadata. So the metadata file is pointing to a new snapshot, which is this particular snapshot, which is basically a manifest list. So this metadata file is pointing to this manifest list, which is pointing to this manifest file, and this manifest file has information about all the data files. And it also shows you the manifest list here. So if you see, this is the manifest list, order items, snap, the file or the object that I was talking about, snap 03128 ends with .avro. Right, and we have metadata log also. So this was the earlier metadata log. Anyway, so this is the metadata file, second metadata file. Now let's take a look at the data file. So if we go to the data folder, I should be able to see these multiple folders actually. And each folder would contain a Parquet file. So all of them is basically 22:55:29. If I look at the size, so the size is approximately 118 MB, right? So if I look at, let's say this one also, it should be 117 MB, and this is when it was created. So these are all Parquet files. Why so many Parquet files? Because as I said, right, Athena is a distributed processing, so it is using MPP, and all of them are writing to a single its own Parquet file. So that's why we have so many Parquet files. So just remember the number, we have 16 objects, right? So now what will I do? I will go ahead and make some changes. We have done an insert, we have done multiple inserts rather. Now let me go ahead and just delete one row. Let me select 5 rows first, and these are the rows, right? So we have order ID and product ID. Now what am I going to do? I'll be deleting the row with this order ID, which was not possible earlier. And with this Iceberg or open table format, I can do that. So delete from, now remember this is string, so let me go ahead and delete it. So I should not be able to see, I don't know how many rows would be gone. So 1.51 GB was scanned and the row was deleted. Let's do a count star because we had loaded approximately 200 million rows. Let's see how many rows are left. All right, 3 rows have been deleted. So I think with this order ID, we had 3 rows. 3 rows are gone. Let's go back to S3. Let's take a look at the metadata folder first, and we had 4 objects earlier. Now of course we have a lot of other objects. We have a metadata. So this is the new metadata which was created at 2301, which is pointing to this manifest list, right, to M0 Avro, which is the new manifest list, which might be pointing, which is pointing to this one of these snapshots, which is this one, 257, 46547, and it is pointing to this particular manifest list, which is m0.avro. So one more metadata file got created, one more manifest file got created, and one more manifest list got created. Let's take a look at the data folder. So if you remember, we had 16 objects. Now we have 19 objects, right? So it seems like 3 objects have been created. And let's see the time. Okay, this is the latest one. So if you see, the size is only 1 KB, and this is also a Parquet file. This is a delete file because it was created recently. And similarly, I think this is the next one, which would also be, okay, this is not a delete file. So there might be some other delete files also. So this is the other delete file, which is also of 1 KB size, and this is also a Parquet file. And there would be one more, so there are multiple delete files. So we did some insert and we did some modifications. We deleted 3 rows and it created 3 delete files and then created a new metadata file. Now what will I do is I'll go ahead and update a row. So let me get the first 5 records. Now what will I do? I'll update the order ID with this particular value. Now let's do a count star and let's see how many rows are there with this order ID. Okay, there is only one row. So now what will I do? I will update the table. So let me execute this update command and it should update only one row. So the query is done, and let me go back to the metadata folder, not the data folder. So let's just take a look at the data folder. So it is 21 now. And now if I go to the metadata folder, so we have one more metadata file, we have one more manifest list, one more manifest file. So it started with M1. All right, so this is how basically Iceberg maintains changes of all the tables. And now if I do a select with this order ID, I should be able to see that the product ID has been changed to 3iam.in. So as you can see, the order ID is this one and the product ID is 3iam.in. Now, one more question that might pop into your head is that earlier we had 19 objects, now we have 21. Why that is the case? If you remember, I told you that update is basically a delete followed by an insert. So the existing row is deleted and a new row is inserted. So that's why we have 2 more objects. Now there might be a question that is it the case that for every update, insert, delete there would be one file created? The answer is no. It's not that for every update, insert, delete one file would be created. Iceberg would handle it itself. So if you're doing a lot of updates at one go, then those will be actually put in a single file. So that's how Iceberg works. Now, as I already told you about delete files, so what are delete files? Files that contain only the changes. And there are 2 types of tables in Iceberg, by the way. We have something called copy on write and merge on read. So let me tell you what are the differences between the two. The first one, or copy on write, in this case, let's say we have a data file of 100 GB and let's say we're inserting one row or deleting one row or updating one row. So in that case, what would happen? A new file would be created. So the entire file would be changed or replaced. So even if you are making, let's say, a few KB of changes, Iceberg would write the entire file or it would rewrite the entire file. Let's say you are doing again one more delete or update or insert, the same file would be rewritten again. So this is what copy on write is. As you can see, this is not good for write heavy applications or write heavy lake houses. So if there are a lot of writes, you can imagine the amount of size that your table would be. Even if you have 100 GB and if you have made let's say only a few GB of changes, your table size or your storage size rather would go to few hundred GBs. Obviously, it is something that is not desirable. And that's where merge on read tables come into picture. So in that case, what would happen? You have, let's say, the data file, and then all the modifications would be saved in the delete files, or you can call it as delta files also, which would contain all the changes that you have made on that particular table. And as you have seen in Iceberg follows merge on read in on Athena. So all the modifications were getting captured in delete files, which were also in Parquet. All right, so now coming back to acid. So we started the topic with acid. So you already know what acid is, right? So it's atomicity, consistency, isolation, and durability. We have talked about acid in Redshift. So if you want to learn more about acid, please go through the Redshift video. In Athena, we do not have any begin transaction or end transaction. The row level modifications are acid in nature. So if you have multiple concurrent applications, and let's say if they're trying to modify the same row, then that row would come under acid semantics. We do not have acid blocks, or we do not have transaction blocks wherein we start a transaction and then either commit the transaction or roll it back. So there's no begin transaction and followed by commit or rollback. So acid in Athena using Iceberg only supports or only covers row level modifications, and concurrent users can write records. Also, we have something called optimize and a vacuum. So what optimize would do, it will optimize row in an Iceberg table by rewriting data files into a more optimized layout based on the size and number of associated delete files. What is meant by this particular statement? It means that over a period of time, you might be having, let's say, one or more data files in Parquet, but if you have done a lot of modifications, your number of delete files would be pretty huge. So what optimize would do, optimize would basically merge all those delete files and the data files and would create a new set of data files. That's what optimize does. And this is the command optimize followed by the table name. And vacuum actually expires snapshots and removes the unused files from the metadata folder. And also it removes the files from the data folder, thereby reducing the storage consumption. So these are the two things that you do after, let's say, once a month or maybe once a quarter, etc. So if your writes are too heavy as in compared to relatively to a data warehousing system, then maybe you'd run optimize and vacuum once a month, or maybe twice a month. It will go ahead and expire the snapshots and then remove the unused files. And this is the syntax, vacuum followed by the table name.